Okay, so in chapter 23, we're going to talk about blood vessels and circulation. And just an overview of this chapter, we're going to start out with the anatomy of blood vessels. Like what makes a blood vessel, what are the layers, and what are the functions of these layers. Then we'll move on to talk about things like blood pressure and how it's regulated. Then we'll talk about systemic and pulmonary circulation, a review of the heart, systemic and pulmonary circulation, and then get a little bit on fetal circulation as well near the end, because we know that as a fetus you're not using your lungs, so their blood flow is a little different than someone who's born. So in terms of blood vessels, we already talked about how arteries carry blood away from the heart, veins carry blood to the heart. And it's not true that all arteries carry oxygenated blood or all veins carry deoxygenated blood. So a better definition is that arteries carry blood away from the heart, right, towards more distant sites of your body. Veins return blood back to the heart. So it's basically bringing blood back to the heart. And there's lots of different types of blood vessels, though. So we can have arteries, veins, and capillaries, too. Capillaries are the most abundant of your blood vessels, but they're also the smallest and the thinnest. So it's at the level of capillaries where nutrients and wastes and gases and other things can be exchanged because the vessel walls are very thin. Really, the function of arteries and veins is to help transport that blood, but the magic happens at capillaries, and we'll talk about that a little bit later. So we're going to first talk about the blood vessel tunics. And so tunic just means layer. And the first blood vessel tunic we're going to talk about is tunica intima. Now, think about the name, tunica intima. Well, it sounds like it's the most intimate, right? It's the deepest. So tunica intima is what lines the lumen, or the inside space of your blood vessel. And this tunica intima is made of a simple squamous type of epithelium we call endothelium. And endothelium is basically what lines the inside of that blood vessel and provides a nice sort of structure, and also is very smooth, so it prevents turbulence of blood, so you're less likely to get blood clots. Now, there is a subendothelial layer of areolar connective tissue that helps nourish this endothelium of the tunica intima. But again, the tunica intima is just a very thin layer of tissue, basically a simple squamous epithelium. In fact, once you start getting down to capillaries, capillaries are basically just made of like a tunica intima. Okay? Now, in some of your larger vessels, you're going to have a tunica media, and the media is the smooth muscle layer of these vessels. So both veins and arteries have a tunica media, and they're primarily made of smooth muscle, which we've learned about was conscious or unconscious. Unconscious, right? So if we know that it's unconscious, it's going to be regulated by the autonomic or automatic nervous system, like your sympathetic and parasympathetic nervous systems can regulate the activity of this muscle. So the effect of sympathetic nervous system on a lot of the vessels of your body is vasoconstriction. Not all of them, but many of them. So that when you're sympathetically active, you'll get vasoconstriction, where basically the tunica media will constrict or contract, which causes the vessel lumen to decrease in size. And we've talked about how that would increase resistance and decrease blood flow. Now, opposite to that, the parasympathetic nervous system stimulates vasodilation in many parts of your body. Not always, but in many areas. And this vasodilation occurs when the smooth muscle relaxes. You get a wider vessel lumen, so you increase the diameter of that lumen. This is going to decrease resistance and increase flow in those vessels. Now, that's a smooth muscle layer in the middle, tunica media. Tunica externa is what lines the very outside of that blood vessel, and it's basically just connective tissue that's really dense, fibrous, and it helps hold that vessel to the surrounding tissues. Okay, it's just a nice, tough kind of tissue that surrounds the outside of the vessel. Now, it turns out that some of your larger and thicker vessels have their own blood vessels. Like with the heart, we talked about how the heart has its own coronary circulation. Well, some of your larger blood vessels also have their own blood vessels within the vessel itself. We call that vasovassorum, which is mentioned here. So you're going to find vasovassorum in the tunica externa of some of your larger blood vessels, like your aorta, the vena cava. They're so big, although they're transporting blood, these tissues are thick enough to where they actually need their own blood flow from within the tissues. And that's vasovassorum, which is like the coronary circulation, but for blood vessels. Now, looking at this, you guys, this slide shows a summary of the structure of arteries and veins. And so looking at the difference between an artery and a vein, you can see, first of all, that arteries are much thicker. Just the first glance. Arteries appear much thicker than veins. And the lumen of a vein also appears to be wider than the lumen of an artery. And this is true for the most part. Now, veins also have valves, whereas arteries don't. So these valves prevent backflow of blood, and they allow for a unidirectional flow of venous blood back towards the heart. And these valves are basically just made of that tunica intima, or endothelium. So the valves are super thin tissue. They're delicate, but they're also strong enough to prevent backflow of blood. So just going through those main layers here, we can see a tunica intima, okay, which lines the lumen here. We got tunica media, which is the smooth muscle layer in the middle, and then tunica externa on the outside. You'll notice that the externa has all these little red and blue dots within it. That's representing the vasa vasorum. And the vasa vasorum are smaller blood vessels within that tunica externa, because it can be so thick that it actually needs its own blood supply. Now, comparing the difference between these layers in a vein versus an artery, you can see that in an artery, the tunica media is much thicker. You have a lot more smooth muscle in an artery than you do in a vein, like in terms of thickness. The tunica externa is not as thick. We still have a tunica intima, but there's no valves in an artery. Now, you might wonder, why are arteries thicker than veins? Well, arteries carry higher pressure. If arteries are carrying blood away from the heart, that means they're going to be the closest to where pressure is generated, so they're going to experience the highest amount of blood pressure. Whereas veins, if they're carrying blood back to the heart, they're going to be farther away from where pressure is generated, so that their pressure is much lower. In fact, some of your larger veins have a blood pressure that's close to 0. There's almost no pressure in these veins. Like for the vena cava that drain into your heart, their blood pressure is almost 0. So they don't need to have thick walls, right? They're just there to sort of help transport blood, they don't have to support blood pressure from the inside that could have a tendency to possibly rip that vessel. That's why arteries are much thicker. Now, arteries will branch into smaller and smaller branches until they eventually lead into a capillary bed. Now, looking at the structure of a capillary, we see that there's not really much of a tunica externa or tunica media. So we don't have that thick outer fibrous layer, nor do we have a smooth muscle layer. But basically, the capillaries here are just a tunica intima. You have an endothelium with a basement membrane. That's it. And what's nice is that the reason why I want these capillaries to be so thin is that it helps transport nutrients across that vessel wall. Because these vessels are so thin, nutrients can be exchanged across the bloodstream really easily. And this occurs due to the fact that they're so thin. Eventually, these capillaries will converge back into veins, and then these veins will carry blood back towards the heart. Now, just looking at the microscopic anatomy of an artery and a vein, looking here, you guys, you've got a vessel up top and a vessel down below. Which one do you guys think is the vein? Up top, yeah. You can tell because
There's a bigger lumen.
Much bigger lumen. How about the wall?
Thinner.
Thinner walls, good. So big lumen, thin walls. You tell this is an artery because you have a smaller lumen, super thick wall. In fact, what layer is really thick in an artery that makes it so? Yeah, tunica media. So all of this is the smooth muscle layer, tunica media. Now this is important to note because the smooth muscle regulates the diameter of this lumen, and the diameter of that lumen changes the resistance and flow of that vessel. And so you might wonder, well, why would you want to change the resistance and flow in arteries? Well, you might want to increase blood pressure, or you might want to increase blood flow to a particular organ. And so you can do this by changing the contracted state of the smooth muscle you find in arteries. Now, veins have smooth muscle because you can get venoconstriction too. Venoconstriction is where veins can constrict and help squeeze blood back towards your heart. So if you wanted to increase your venous return to the heart to increase cardiac output, you can actually have this smooth muscle constrict, and that can help squeeze some blood back towards your heart. Now here it looks like there's less blood because there's a lot of empty space here. It's just because the way this slide was prepared. But it turns out that veins hold a significant amount more blood than arteries do. Because first of all, veins are more abundant than arteries. And veins have a wider lumen, so that actually store up to 60 to 70% of your blood's volume at rest. Veins do. Which means that only about 40 to 30% of the rest of your blood is actually found in arteries. So most of your blood's found at the venous end. So what this slide shows you guys is just a comparison of arteries and veins. Which one has a more narrow lumen? Arteries, right? Which one has a thicker wall? Arteries, good. Which one holds more blood? Veins, good. Which one has more structure? Like if it has more of a rounded shape. Arteries would, exactly. Because arteries have thicker walls, they're going to have more structure to them. Veins, on the other hand, are so thinly walled that if there's no blood in the vein, it just collapses because there's not even enough tissue to really support the structure of that vein itself. Now, when we go to the coroner's office or in dissection, you guys will see these veins, and they don't even look rounded. They just look like a little flattened, like deflated Ziploc bag or something like that. You know, like they don't have much structure to them at all because they're so thin. Which one has more elastic fibers?
Artery.
Yeah, arteries would, because they need to stretch more, right? They're having to resist that blood pressure, which means that they need more elastic fibers and more collagen fibers because they need to be tougher. Which ones have valves? Veins, yeah, because veins need these valves to prevent backflow. The pressure in veins is so low that you could see that blood flow could reverse. It could go backwards. But to prevent this backflow, you have veins. Most of your veins have valves. Some of the really small veins and some of your really large veins lack valves, but the medium-sized veins have a lot of valves, and they're pretty frequent. Like, you're going to find them every several millimeters or so. Now, blood pressure is higher in an artery or vein? Artery, because arteries carry blood away from the heart, and the heart is what generates blood pressure. So if arteries are coming away from the heart, then those vessels, which are coming away from the heart, then are closest to the place where blood pressure is generated, so you can expect that it's going to be the highest there. Veins bring blood back to the heart, which means they're very far from the heart in terms of blood flow. And because they're so far away, their pressure is going to be significantly lower. Which one has typically is oxygenated? Arteries, yeah. Arteries are typically carry oxygenated blood. Veins typically carry deoxygenated blood, but there are some exceptions to that rule. The pulmonary arteries, which carry blood to your lungs, those carry deoxygenated blood. And the pulmonary veins, which carry blood back to your heart from your lungs, carry oxygenated blood. And we'll talk about later with fetal circulation, the umbilical veins, which carry blood away from the placenta back towards the fetus through the umbilical cord, that also carries oxygenated blood. Because that's where the blood gets oxygenated in the fetus, is at the level of the placenta, not the lungs. So those are some examples of veins and arteries that carry oxygenated or deoxygenated blood. You have a question?
Yeah. So for the structure of those pulmonary arteries and veins,
Yeah.
are they flip-flop are they just both larger and thicker because they're so close to the heart?
Yeah, you got it. So what's interesting is that although the pulmonary artery carries deoxygenated blood, it still has high pressure, right? Because it's coming from the right ventricle, so that it still needs to have thicker walls like the rest of the arteries. So it just happens to carry deoxygenated blood. And then the pulmonary veins, which are carrying blood back to the left atrium, also have low blood pressure because they're just coming from the lungs. And so their walls are thinner, even though it's carrying oxygenated blood. That's a good question. Now, there's several different types of arteries, you guys. We'll talk about elastic arteries, muscular arteries, and arterioles. The elastic arteries are the largest of your arteries. Like earlier we learned about the aorta and its associated branches, right? Like the brachiocephalic trunk, the left common carotid, left subclavian. Like those are examples of some elastic arteries. They need to be more stretchable, right? Because there's such large changes in blood pressure, these vessels need to stretch and expand for that change in blood pressure and then recoil back to a resting shape. And what makes them more elastic is just more elastic fibers. So an elastic artery is going to find a lot more like internal elastic lamina, external elastic lamina, basically just extra layers of elastic tissue that makes these vessels more stretchable. Now, second to that, and what's typically smaller, are the muscular arteries. These muscular arteries have less elastic tissue, but have a lot more smooth muscle. So these muscular arteries are involved with helping to regulate things like blood pressure and blood flow at the level of like vasoconstriction, vasodilation, because they can change their vessel diameter based on that smooth muscle, right? Hence the name muscular arteries. Now, muscular arteries eventually branch into what we call arterioles. Arterioles are microscopic, and they precede the capillary bed. So arterioles are technically the last artery you can have before you get to a capillary. Arterioles are microscopically small. You might be able to see some with an unaided eye, but they're very, very tiny. And these have pretty thin walls. They do have some smooth muscle, so arterioles are also involved in regulating blood pressure and blood flow, but arterioles carry lower blood pressure because the tendency is that blood pressure will decline as you go from the larger arteries, like your elastic arteries, down towards the arterioles, capillaries, and then veins. The reason why blood pressure diminishes is that force diminishes over time and distance. So as the blood moves to smaller and smaller vessels, the pressure gets lower and lower and lower. And so we'll come back to that later too. So what this slide shows then are a comparison of your larger arteries, capillaries, and then veins. So we know that it goes from elastic arteries to muscular arteries to arterioles. Those lead into capillaries, which then can lead back into a venule, small to medium-sized vein, and a large vein, like the vena cava. So this just shows your vascular system side by side, which is pretty amazing. And there are millions of miles of blood vessels in your body. So it's pretty amazing how much flow and the intricacy of our cardiovascular system at the microscopic level is kind of unfathomable. You know, there's so many millions of miles of vessels just in your body. It's actually pretty cool. So these elastic arteries are the largest, right? An example would be like your aorta. They're more bendable, more flexible, and they're more elastic so they can recoil back to a resting shape. What's the layer of tissue that lines the inside of vessels called? Tunica intima. What's it made of? Simple squamous epithelium, which we call endothelium, with a little bit of loose areolar connective tissue deep to that. Then we can have an internal elastic lamina, which is what they're showing here in yellow. And then deep to that, or sort of more external, we got tunica media. What's that made of? Smooth muscle and some elastic tissue as well. And then outside of that, we have tunica externa. What's that made of?
Elastic fibers and collagen.
Yeah, elastic fibers, collagen. It's that nice fibrous tissue. What's the point of having a tunica externa? Why not just end it with media?
So they can structure.
Gives it some more structure. Gives it some more external support. They're more stretchable. Good. And it can attach to nearby structures. You know, like your vessels don't just roll around inside your tissues. They're attached to nearby structure. Like they're attached to superficial and deep fascia or like nearby fibers. So it helps hold them in place. That way your vessels don't just start moving around a whole lot. You know, if that's somehow disrupted, yeah, vessels can move. You hear about like veins that roll or arteries that roll, right? But that's because their tunica externa is not well attached to the nearby tissue. But for the most part, it should be throughout your body. What's significant about muscular arteries? Why do we call it that?
Because if there's more smooth muscle.
A lot of smooth muscle. Good.
Less elastic.
Less elastic tissue. You can see it's more sparse here. And then what about arterioles? Can you see these with the naked eye? Not really. No, they're going to be microscopically small. And then those arterioles are the last type of blood vessel. But they do, or I'm sorry, last type of artery. But they do help regulate blood pressure. And they precede the capillary bed. Now, what's significant about capillaries? You got it. Gas, nutrient exchange, and waste exchange. So you can help eliminate wastes from tissues. And now, how many layers do capillaries have?
2.
Basically, just a tunica intima, right? So, bless you. What you have then is the tunica intima, and then some basement membrane. That's it. So you're not going to find a media. You're not going to find an externa. Capillaries are super thin, which makes them very well able to help transport materials across the vessel wall. Capillaries will reconverge into venules, like the smallest of your veins. Venules will converge to small and medium-sized veins, which have valves, prevent backflow. What are the valves made of?
Simple squamous endothelium.
Endothelium as well. Good. So it's simple squamous epithelium. And then the small to medium-sized veins will converge into large veins like your vena cava. Cool. So elastic arteries are the strongest of your arteries. You know, some examples would be like your aorta, pulmonary arteries, brachiocephalic arteries, common carotids, subclavians. They're more stretchable. And it makes sense because these are some of the ones that are closest to your heart, which means they're getting the largest fluctuations in blood pressure, like systolic versus diastolic pressure. Differences will be highest in these elastic arteries. So you're going to find elastic fibers in all 3 layers or tunics, which help these vessels stretch under increased pressure. And eventually these elastic arteries will branch into smaller muscular arteries. So this is showing the lumen of or the wall of an elastic artery. You'll notice here there's a lot of dark lines that kind of go across this tissue. This is all elastic tissue you're going to find within the vessel wall. You got a muscular artery here. You can see the wall is much thinner, but it has a lot of smooth muscle, so it's involved in blood flow, blood pressure regulation. And then an arteriole, which still has a thick wall. It's not thin enough to be involved with a lot of nutrient and gas exchange, but it does have some smooth muscle, so arterioles are also involved in regulating blood pressure and blood flow. Now, those muscular arteries do have elastic tissue as well, so we have internal and external elastic lamina. So muscular arteries are stretchable, but they do have a thicker tunica media, which is why we call them muscular arteries. Arterioles are the smallest of your arteries. They have less than 6 cell layers of different cells of smooth muscle and their tunica intima. So they're pretty thin. Like an average cell thickness is maybe 10 microns or so. So you're talking about 60 microns, which is basically, how do you describe that? That would be like a little bit less than 1/10 of a millimeter in diameter. So it's pretty thin. And a millimeter is about the thickness of a thick hair. Think about 10% of that. Well, the arterial thickness is actually less than 10% of that thickness. So lots of numbers, but basically my point is that they're super thin. Now, these arterioles get innervation or nerve supply from both your sympathetic and parasympathetic nervous system. The function of your sympathetic nervous system on arterioles is to stimulate vasoconstriction. So they're going to cause the smooth muscle in these arterioles to contract, which causes the vessels to constrict. It makes the lumen or the diameter of that vessel more narrow, which increases resistance. If you increase resistance, then you increase blood pressure. Good. If you increase resistance, what does that do to blood flow? Decreases flow. Exactly. So although you're going to increase blood pressure in a particular tissue, you will decrease blood flow downstream of that constriction. Now, the parasympathetic nervous system does the opposite. So the parasympathetic nervous system will cause vasodilation. And if you vasodilate, it makes the lumen more wide because the smooth muscle is relaxing. If that lumen is wider, then you have less resistance and more flow. But if you decrease resistance, what does that do to blood pressure? Decreases blood pressure. Good. So that one of the effects of the parasympathetic nervous system would be to decrease blood pressure. Capillaries are the smallest of your blood vessels, you guys. Their diameter is actually just slightly larger than one red blood cell. So your capillaries are about only as wide as one red blood cell that's barely squeezed through. The wall of a capillary is basically one cell layer thick. It's a simple squamous epithelium with a little bit of basement membrane deep to that. So you can imagine that these vessels aren't really strong, but they're also microscopically small. And these are the ones that are going to be involved in exchange of nutrients and wastes. So metabolic exchange occurs between blood and tissue only at the level of the capillary. You're not going to get exchange of nutrients between arteries and tissues or veins and tissues, just capillaries, because these are the thin enough to actually be involved in exchange of nutrients. Capillary beds are basically just wide areas of capillaries where these small vessels can kind of branch out into a big old blanket of vessels. We call it a capillary bed. In fact, it looks like a big old net of blood vessels. So these capillary beds will basically spread out through and over and within a tissue, and that's what's going to help allow for nutrient exchange basically from capillary or blood that's in the capillary as well as your tissues. Now, looking at the structure of a capillary bed, we see that we have an arterial end and a venule end, and blood's going to flow from the arterial end across the capillary towards the venule end. Okay. Now, all these capillaries have what we call a meta-arteriole, which is sort of what precedes the capillary bed, and that will actually lead into a thoroughfare channel, which basically can just go straight through the capillary. So think of the thoroughfare channel as sort of just like the main line of the capillary. But coming off this thoroughfare channel, we got all these little side branches of capillaries, and these side branches have what we call precapillary sphincters. And what these precapillary sphincters do is they're just basically little rings of smooth muscle that can help regulate blood flow through these capillaries. So let's say if you were sympathetically active and you didn't want to have a lot of blood flow to your digestive organs. Well, what you can do then is actually cause these precapillary sphincters to constrict. Once these constrict, it's going to reduce blood flow through these little side branches of capillaries, which are called true capillaries. That's what we see here. So you can reduce blood flow through this area of the capillary. Now you can still get some blood flowing through the thoroughfare channel here, but you won't get as much blood flow because there's less space for blood to flow, which basically means that if blood's flowing through this arteriole, some of it might go through this thoroughfare channel, but the rest will be diverted away. It'll just keep flowing through. It'll go to some other tissue. Like if you're sympathetically active, that would allow then for blood to go to muscle or something else, skeletal muscle, which could be involved in your sympathetic response. So these precapillary sphincters can help regulate the amount of blood flow through capillaries. And I'll give you guys an example of where else this is used. In your lungs, only about 25% of your lung tissue ever gets a full amount of blood flow. So 25% of your lungs only get their blood flow. The rest isn't currently getting blood flow, but it's constantly changing. It's modifying. It's not like a part of your lung never gets blood flow. It's just that at any moment in time, only 25% of your lungs are perfused because blood is sent to the areas where you get the best gas exchange with lungs. So what we can do then is let's say if this is a capillary bed near a part of your lung that's plugged with mucus. Well, instead of sending blood flow to that part of your lung that's plugged with mucus, and it wouldn't really be involved with gas exchange, you can constrict these precapillary sphincters and then have that blood go to a different part of your lung, which then could get better gas exchange, which is more efficient. So it's a really cool way about improving efficiency and blood flow in your body. Now, in terms of types of capillaries, we got three main types. We got continuous, fenestrated, and sinusoidal. The continuous capillaries are the most common variety. Basically, we have a continuous endothelium or simple squamous epithelium inside the blood vessels. These cells are really tightly held together with tight junctions. If y'all remember going back to chapter 3 of cells, we talked about how tight junctions hold cells together very strongly, but also waterproof those cells, so it prevents water from passing between them. Now, the continuous variety are the most abundant, and they have a lot of tight junctions, which helps waterproof these vessels so they're not as leaky. You don't want to leak a lot of fluid from your capillaries into your tissues. The fenestrated variety contains these pores, which we call fenestrations, and these are small little pores that go through the cells of the capillary itself. These pores are small enough to allow things like water and small ions to cross the capillary wall, but larger substances and cells can't cross the fenestration. So you're going to find fenestrated types of capillaries common in places like your kidneys, where you want to have filtration of blood to form urine. And then last but not least, you guys, the sinusoidal capillary. Bless you. These sinusoidal capillaries are some of the least abundant, but they have these large gaps in the capillary wall called sinusoids. And these sinusoidal capillaries have such large gaps that entire blood cells can actually enter and leave the bloodstream across this vessel wall. So where do you guys think in the body might you want to have a sinusoidal capillary where you have blood cells entering or exiting the blood vessel? What do you guys think? Yeah, perfect. Bone marrow. You got it. Because remember, in red bone marrow, you're forming new blood cells. Well, how do those blood cells get into your bloodstream? Well, they have to be pushed in somehow, and they get pushed in through the sinusoidal type of capillary here.
Maybe your liver?
Yeah, your liver's got them too. And your spleen. Exactly. Because those are both organs that help break down damaged red blood cells. But to do that, they have to leave the bloodstream, and then they're engulfed by immune cells outside of those vessels. And these sinusoidal capillaries have a discontinuous basement membrane, which basically allows for large clefts or gaps in the vessel wall. So what we see here on this slide then is from left to right, the different types of capillaries. So you have the continuous, fenestrated, and sinusoidal. You can see the continuous capillaries have these simple squamous cells that are very strongly held together with tight junctions, and they have a complete basement membrane. So these are the least leaky, like the variety of these continuous capillaries are the least leaky. And you're going to find these. This is the main type of capillary in the brain to help make the blood-brain barrier. Remember, the blood-brain barrier helps prevent substances in your bloodstream from just escaping into your brain tissue. And you're going to want a continuous capillary to help prevent that. Now, the fenestrated variety of capillaries you'll find in places like the kidney, which is involved in filtering blood. In fact, every kidney gets about 7 liters of blood every hour. So you can filter that much blood every hour. So it means that basically your entire blood volume is filtered once every hour. So it keeps your blood fairly clean in that sense. So it's actually pretty cool. But the way you can filter that much blood is through these fenestrations or pores. And these pores allow smaller substances like water, wastes, other ions to slip through. That way your kidney can help eliminate those wastes. But other larger things like cells and large plasma proteins, bless you, can't slip through those fenestrations. These sinusoidal capillaries have large clefts here and an incomplete basement membrane, so that entire cells can slip through. These aren't as abundant, but they're also the most leaky variety of capillary. And you're going to find this in places like red bone marrow, your liver, and your spleen, where blood cells need to enter and exit the bloodstream pretty frequently.